All right, everyone, good morning. I've just hit the record button, so welcome. What we are going to do is today is just a review day. So much like we did last review day, I am going to do a polling session. We'll do some, just going to set it up here. Okay, there we go. I'm just posting the link to the chat. There we go. There's a link in the chat. And I will drag my Safari window over as well. We're going to do a polling session. I'm also, you feel free to ask questions if you like. There's the URL posted in the chat link, but also here as well. It's mathmatize.com/polls, and then our special polling ID. Do you need to memorize certain moves to produce 3 cycles or corner turns of the cube? No. I'm not going to expect you to memorize any of the cube specific moves. If I'm going to ask a commutator or conjugation question, then it'll be of the nature of the kinds of questions that were done in chapters 13 and 14. Like the review question has, in some sense. Here's an initial move on a cube. You're going to do the commutator with the U move, explain why this, what pieces this will move, etc. That could be a possible type of question. But no, I'm not going to ask you cube specific sequences, because that's technically, I would consider that falling into chapter 19, the basics of the Rubik's Cube. Okay, so if you've clicked the link in the chat window, I will post it again just in case someone joined us and the chat, it doesn't show them a history. They get it whenever you get in, you get whatever is currently in the chat as soon as you log in, and not stuff before. So if you just joined us, there's the link in the chat. And I've got the first question up. We'll go through a couple of these, and you feel free to ask questions and the like. So this first question, it's now live, and you can go ahead and respond. I would say I'm going to move this away from my screen just so that you can focus on your own browser. I don't want you to have to look at too many things. So there's nothing on my screen share now. Just go ahead and look at your browser window and the polling question in your browser window. This question is asking about the definition of a group. So we've been using groups since chapter 10, and we have a definition of what a group is. Select only the parts below from the 9 things I've written there. Select only the parts that are a part of the definition of a group. If you hit submit, so this came up last time, if you hit submit and then you realize, oh, I didn't want to do that, I wanted to change my answer, and you don't see a way to resubmit, just hit refresh, just refresh the page. Refresh the page and you'll get a fresh page with the question, and then you could resubmit your answers. That's the way to do it. Just a page refresh and allows you to resubmit again. All right, for those just joining us, we are doing a polling session. And the link's in the chat. If you don't see it, just ask me to repost. I don't want to load up my screen share with other images because I want you to focus on the poll question itself. Yep, I certainly can. I'll repost there you go. Link's been reposted. I'll post it for everyone. I see that was a direct message. So there's the link reposted for everyone. All right, we're still about 15 responses short of the full group. So I'll give you a few more, about another minute or so to get your response in. So you're selecting all that apply. We've got the definition of a group. So it starts with let G be a set, and then some stuff about what you need to require on that set G to have. Select all the relevant parts of the definition. Yep. There the link is posted one more time. So go ahead and click the link. And so what are the relevant parts of the definition? And be sure not to, be sure not to click the thing. I was about to say something really, really silly, but what I meant to say was, be sure not to click on something that you're clicking on it just because you believe it's true. You know, like, yeah, that's true. This is a more question about what is part of the definition, because there may be true statements that are listed there, but they're not part of the definition. They are consequences of the definition. They are theorems that follow from the statement of the definition. So some of those distractors might be theorems that result or statements that are true because of the definition of a group. They are not part of the definition. So remember to select only the things that are part of the definition. If you want to resubmit your responses, you can just refresh the page. Yeah, so refresh the page, and you can go ahead and click the parts that are only a part of the definition. All right, looks like we're getting all the responses in. A couple more just came in. We are perfect. We're up, full responses. Okay, not sure how that happens. We've got more responses. Maybe I think the page refresh actually counts it again. I was going to say, I don't know how we got more responses than we have people, but yeah, a refresh page, I think just comes in as an additional response. All right, so I'm going to close the pull down and we will see the results. And the results should now be showing on your page. There are 4 parts of the definition of a group. There are really, a group G is a set, and there's also a binary operation on that set. Basically, it's a function which we call star, which takes 2 elements of the set and uses them to combine together to produce another element of the set. So that's the first part, is a group consists of a set G with a binary operation, star, going from G cross G to G. So that's our operation part of it. That's our multiplication, if you will. And then there's there's 3 properties that it has to satisfy. We call them associative, identity, and inverse. And we read down the list, and there's the associative property. That's the one that says A star bracket B star C is equal to, and then parentheses, A star B star C is true for all A, B, and C, and G. So it's associative. And then there's the identity. So there is an E in G such that A star E is equal to E star A is equal to A for all A and G. So there's this identity element. And lastly, for each element A, there is another element B such that A star B is the same as B star A, and both of those are equal to E, the identity. So that's the essence of a group, a binary operation that satisfies associative, identity, and inverse. Are there any questions with this one? And I'll give you a big hint right now. You're going to pick up a few points on the exam if you can write down this definition of a group. A set G with a binary operation from a star from G cross G to G, which satisfies three properties. The associative property, which is written there, the identity property, there exists an E that when you multiply to any element, just returns that element, and the inverse property. For any element, there's an inverse. Are there any questions with this one? So you'll pick up a couple of points on the midterm if you just take a few minutes and study the definition of a group in chapter 10 of the lecture notes or the booklet. So you say in the chat, I noticed that there's theorem 10.1.1, uniqueness of inverse. It claims that for each element A, there's a unique B, such that A star B equals B star A equals E. That means that the uniqueness of an inverse, though it's not part of the definition of a group, it actually turns out to be a consequence of these definitions. So inverses are unique. And so that is one of the options that I had there. It says the inverse of an element is unique. It is true. Oh, thanks for reposting, Hazim. Thanks for reposting. So the inverses are unique, and so is the identity. Identity is unique. So those are both true statements. They are just not part of the definition of a group. They are consequences of the definition. And it's nice to separate consequences from the actual definition, because that way we don't have to overload the definition with saying things like, oh, the inverse is unique, the identity is unique, and these other statements like A star B is equal to A star C. That means that B is equal to C. That's a true statement, but we don't have to include that in the definition because it follows as a consequence of the definition of a group. So yeah, good question. Yeah, so the identity is unique is true, but this is not, the question is not asking you to select all the statements that are true. It's asking you to select the statements that are part of the definition. So in fact, every statement up there is true. It's just not part of the definition of the group. The ones that are not part of the definition are actually consequences of the definition. Actually, I shouldn't say all of them are true. There's one statement, A star B is equal to B star A for all A and B and G. That's not true for a group in general. That's only true for commutative groups. What is a unary function? So a binary function's two inputs, unary one input, like a unicycle, one wheel. So a unary function is a function with one input. And so you can kind of think of it as, well, the inverse is a function. It takes one input in, and then it returns the inverse. Yeah, that was just a funny distractor. I wanted to throw the word unary in there just for fun. But yeah, it's as opposed to binary is, so let's say functions in calculus 1 and 2 that you may have seen, f of x is equal to something involving x. Those are unary functions, one variable in, one variable out. Binary functions, two variables in, one out. Ternary functions, three variables in, one out, that kind of thing. All right, let's go to the next question. All right. It's live now. So does Z sub 81 have a subgroup of order 18? Remember, when we reference the order of a subgroup, it really means the size. This is cardinality now. The order of a subgroup is the cardinality of the subgroup, or the cardinality of that set. So does Z81 have a subgroup of order 18 or size 18? All right, another 20 seconds to fire in a response. Five, four, three, two, one. Let's have a look. So the answer is no, it doesn't have a subgroup of size 18. And the reason is, so I'm going to write on the screen. So if you're not looking at the screen sharing, then you won't be able to see this. But on the screen sharing, I'm going to write. So we've got Z81. The size of this group is 81. And we have by Lagrange's theorem. So we had Lagrange's theorem back in chapter 11. We didn't prove it until chapter 18, but we had the result in chapter 11. So we're certainly going to use it because we've been using it on our homework assignments. So Lagrange's theorem says that the size of a subgroup, maybe I'll write it this way, size of a subgroup divides the size of the group, divides size of group. So the question is there a subgroup of size 18? That's really a question is, does 18 divide 81? And the answer is no. 18 is even, 81 is odd, so 18 can't divide into 81. So since it doesn't divide in it, it can't have a subgroup of size 18. All right, so that's Lagrange's theorem. If you're going to have a subgroup of a group, its size has to be of the right type. In other words, it's got to be a divisor of the whole size of the group, the size of the whole group. Just a funny story about this. I wanted to test all of these questions out yesterday while I was making them. And so I had a couple of different browser windows open, and I had my son manning my laptop. And I just said, don't worry about what any of these things mean, just click any arbitrary answer. And so when he got this question, he's like, don't know what Z81 means, don't know what subgroup means, don't know what order means, but he goes, but 18 doesn't divide 81, so I'm clicking no. And I'm like, that's exactly the thought process we wanted. So it was quite funny that the exact thought process you need to do this was what he came up with without having any knowledge of these terms. Okay, so yeah, does it have a subgroup? No, because 18 doesn't divide 81. If it has any chance of being a subgroup, the size has to. He's 12. Yeah, 12. Yeah. All right, let's have a look at the next one. All right. So in Z81, how many elements have order 27? How many elements have order 27? And if you do change your mind, just a reminder, you can refresh the page and resubmit. And I'm just looking at responses coming in, so I'll make one comment because it looks like the majority are answering one way. The answer is not 3. The answer is not 3. So perhaps think about if you had one element of order 27. So that's the answer. 3 is the answer to the question, give an example of an element of order 27. That would be the number 3. 3 would be an element in Z81 that has order 27, because you add 3 to itself over and over and over again, and you have to do it 27 times in order to get to 0. So 3 is an element of order 27, but this question wants to know how many elements are there in total that have order 27. So 3 is one example, but how many others would there be? In fact, how many in total are there? All right, I'm going to close the poll in about 10 seconds. 5, 4, 3, 2, 1. Let's have a look at the result. All right, so the result is 18. So how do we get that? So I'm going back to the screen to do some writing. So I'm on my screen share now. So we are in Z81, and we want to find the number of elements of order 27. So in Z81, the number of elements of order 27 is phi of 27, Euler's phi function, or the number of numbers relatively prime to 27. That's one way to think about it. So I'll do this in a very quick way, and then we'll do it in a more methodical way after. So quick answer is, because Z81, that's a cyclic group. If you have one element of order 27, then the number of elements in total of order 27 is phi of 27. Phi of 27, that's 3 cubed. If you just happen to remember how to compute the phi function for a prime decomposition, then that's 3 squared times 3 minus 1, which is 18. Okay, so that's the quick way to do it. But of course, it requires remembering Euler's phi function and the like. So if we didn't remember that, then the other way to do this is to say, well, 3 is one element of order 27. So that means k times 3 is an element of order 27 if and only if the GCD of k and 27 is 1. So if 3 is one element of order 27, then it generates a subgroup of order 27, and only the multiples of it that are relatively prime to 27 are going to also have order 27. And this is because if I took a number k that had a common factor with 27 and multiplied it to 3, then I've already partially killed 3. So I need to take multiples that aren't. Oh, good question. Would phi of 27 be acceptable on the exam, or will we have to compute it? I'm going to say that that's acceptable. Just leaving it as phi 27, I will accept that, because that does show a higher order of connection with the material. And then you could just leave it. So if the answer turns out to be 527, yeah, I'll say leave it. Well, I'm making that decision right now. Executive decision. We'll accept that, and we don't need to go through and compute it. But let's go ahead and continue. So what would this be? K is an element of order 27. Then all the relatively prime multiples of it would also be. So K is one of. And then I just start listing the relatively prime numbers to 27. So there's 1 is relatively prime, 2 is, 3 is not, 4 is, and 5 is, 6 is not, 7 and 8 are, 9 is not, 10 and 11 are, 12 is not, 13 and 14 are, 15 is not, because basically the ones that are the ones that have a 3 as a common divisor. So 15 is not, 16 and 17 are, 18 is not, 19 and 20 are, 21 is not, 22 and 23 are, 24 is not, and 25 and 26 are. And there are, if we count them up, basically I had 9 pairs there, 1, 2, 4, 5, 7, 8, blah, 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 all the way down. There are 18 in total. So there's the 18 element. Well, sorry, those aren't the 18 elements. Those are the multiples of 3 that would give us the 18 elements. 1 times 3, 2 times 3 are 6, 4 times 3, which is 12, 5 times 3, which is 15. Those are the elements in Z81 that have order 27. Are there any questions with this? So these questions about the, in Z and the U groups in U sub n or in Z sub n, there's divisibility and relative primeness criteria involved in making these decisions. And you just want to be clear on which ones are used where. So there's 18 in total. And you get that by just counting up how many things are relatively prime to 27. All right, let's have a look at the next one. Okay, here I've got a group G, which happens to be a subgroup of S5, and it's got 10 elements, but I've not written down 2 of the elements. Find them. What are the 2 missing elements? And if you click on the boxes next to A and B, you'll get different options for each of those boxes. That way I don't have to worry about whether you put them in one order or the other order, because order doesn't matter for A and B. So in the list for A, one of those is correct, and in the list for B, one of them is correct. What are the missing elements? All right, I'll give you about another 30 seconds or so. Five, 4, 3, 2, 1. Let's have a look. Okay, so you should have gotten your results now. The thing we want to observe is that we've got 10 elements in total. And there's 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry. There should be 12. That should be 12. I've given you 10 elements. There should be 2 more. So I miscounted. I was looking at this going, oh, I think I got more than 10 here. Yeah, there's the 2 missing, and that should round it out to a total of 12 elements. What are the missing 2? Well, if it's a group, then it's got to be closed under multiplication. So we can just start multiplying things together and see which ones are missing. That, I will say, is probably a very time-consuming way to do this. It'll certainly get you the result in the end, but it will eat up a lot of time if you just start randomly multiplying things together. So let's try to think a little bit more strategically about how we can get these missing elements. The first thing to realize is that the inverse of every element's got to be in there. So as a quick check, we can run through and see that the inverse of all elements are in there. This is a product of 2 cycles, so it's its own inverse. Again, it's its own inverse. This 3 cycle, 2, 3, 4, that means 2, 4, 3 has got to be in here. And I scan down the list and I don't see a 2, 4, 3. So that means, oh, that's an option for A. So 2, 4, 3 is my selection for A. So that takes care of the inverse of that one. Then I scan through the rest, 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2. So they're partnered up, 1, 3, 4, 1, 4, 3. Okay, so everything's got its partner now. So I still need to figure out what B is. So those are my options for B. And what I notice is that, okay, if this is going to, if B is going to be this first one, this 4 cycle, then its inverse would have to be in there, 1, 2, 3, 4, but it's not in there. So if I accept B as an answer, then I know that it can't be because the inverse isn't there. Okay, so that's a way to sort of systematically go through these responses. But suppose we didn't have these. I gave you responses just to make it easier to click your submissions, but maybe it was a write-in, like on an exam. It's just write in the answer, figure out where they are. So then we have to be a little bit more strategic in how we do that. So the way I'm going to do that is I'm going to look up here at the list and say, okay, I got all these 3 cycles. I've actually got all of them partnered up now. So I pretty much got all 3 cycles. This B, what could it be? Well, I've got this 2 2 cycles, another 2 2 cycles. This one is 1 is partnered with 2. This one is 1 is partnered with 4. So there's an omission here. It looks like, well, 1 partnered with 3 doesn't seem to appear there. Could 1, 3 be an option? So I'll go to my writing here. And I want to know, is 1, 3 a possible option? Is that a possible option? Is that one that's missing? Well, I have a 1, 2, 3, 4. Can I find a permutation that I can conjugate it by that will get me a 1, 3? Well, maybe to do that, I want to find a permutation that takes 1 to 1, 2 to 3, and then the 3 and 4, this has got to go to 2 and 4. In either order, it doesn't matter. So that's my choices here. So can I find a permutation that does that? I would put the inverse of it over here, and then the fill in the blank, whatever it is, on the right hand side. So let me see. I want 2 to go to 3. And then maybe I'll take 3 to 4, because I know that's one of my permutations I have in that list. 2 goes to 3, 3 goes to 4. That was the first 3 cycle listed. So then if I put that here, then this conjugate ends up being, I can now fill in these details. 3 has gone to 4, and 4 has gone to 2. So this would be that 1 switches with 3, and 2 switches with 4. And that is a product of 2 cycles that does live in that group. And so that's the missing one, 1, 3, 2, 4. And I got it through analyzing cycle structure. So again, with this question, you could go through and start arbitrarily multiplying things together, but there's a lot of things to multiply together, or we can take a step back and sort of think strategically. Other ways to do it could have been, maybe pick a couple of things. Let's see if we can do it in another way, just off the top of my head. And if someone else has a way, just feel free to post it in the chat or turn on your mic and let me know how you did it. Another way to get this product of 2 cycles could be, for example, to pick a couple of elements and try to multiply them together. So maybe I'll take a 1, 2, 3, and I'm going to multiply it by something else. Now the something else I want to multiply it with has got to produce 2 cycles. And so that might be a bit of a challenge, but it means that I probably don't want any more than 1 extra number in the mix. So maybe I'll go with a 2, 3, I don't know, maybe a 2, 3, 4, and let's just see what happens. 1 goes to 2, 2 goes to 3, so 1 goes to 3. And then a 3 goes to 1. That closes it off. Already at this point, just by multiplying these 2 together, again, the way I did it was I just started with one of them, and I tried to use one that had 2 numbers in common with it. Already I know that I've got something that's currently not listed. I don't have a 1, 3 listed. So I know that of my responses, 1, 3, and if there's anything else, is going to be the missing element. And we can go ahead and work out what the missing element is. 2 goes to 3, and 3 goes to 4, so 2 goes to 4, and then 4 goes to 2. So there it is. There's another way to get the missing element. So we're not arbitrarily multiplying any 2 elements. We are being a little bit more strategic in that I'm picking 2 elements that have a lot of overlap in common in hopes that I get something that's useful for me. So a couple of ways to do that. Any questions with this one? Okay, let's have a look at the next problem. I'll drag my browser window over so people who are watching the video after can see which question we're working on. So suppose G is a group with 4 elements, E, A, B, C, and there's its partially filled in Cayley table. What element, so go ahead and fill in the table, and what element should be where X is, and what element should be where Y is. So go ahead, fill out the rest of the table and determine what elements are in each of those spots. looks like the results are now flowing in. We have about another 30 seconds or so to get your response in. All right, 5, 4, 3, 2, 1. Let's have a look. Okay, so the answer in both cases ended up being A. The idea here is we can play a little game of Sudoku, essentially. The first observation to note is that E times E is E, and so that means that E is the identity. And if you just assumed E was the identity because it was, well, after all, it was denoted by E, then that's certainly fine as well. You shouldn't really assume it's the identity. I may have, just encoded the identity as some other letter, but at least E times E equals E. This section right up here tells us that it's the identity. So we can fill in the first row and the first column as follows. And then we just use the property that every row and every column has to contain all of the elements. So we can go across the second row, A, E, C. So the only one missing is B. So B's got to go there. And that B column, the column that has a B in it, actually we'll go the C column. The C column, the only one missing in the C column is A. So that tells us immediately that value for Y is A. And then I can go for, let's say, the B column. The B column, what are our choices? Well, we have A or E and E or A. But because we already have an A in the B row, I can't have an A, so it's got to be an E. And therefore, I can't have an E in that one. It's got to be an A. And so therefore, A's are both of those. Just for purposes of completing the rest of the table, we can fill out that that's got to be a B, and this has got to be a C. And so we're playing with the Cayley table in a Sudoku style, where every row and every column has to contain all the elements. All right, let's have a look at the next question. This is the one I think you've been waiting for. Here's an oval track puzzle. Cut and paste that link into a browser window, solve the oval track puzzle, and select the corresponding phrase that appears when you solved it. So we'll cut and paste this link into a browser window. And go ahead and solve it. Now with the solve, I have made available these sigma 3 and sigma 2s. And I do want you to think in terms of sigma 3s and sigma 2s. We're in the end game. It's really about 3 cycling. So the first thing you want to do is look at that end configuration and just think, what 3 cycle do I need to solve it? Do I need to involve a 2 cycle? I'll only use a 2 cycle if the end permutation is an odd permutation. Otherwise, I'm going to try to avoid 2 cycles because they're really long to do. So what can I do to solve it? Do I do just 3 cycles? Do I need to involve 1 2 cycle, worst case scenario, because it's odd? On the exam, so question in the chat, will you have access to the applets? No, not on the exam. The exam, you won't have access to the applets. But I will indicate that the way I want you to do this kind of a solution on the exam is more about the higher level sort of strategy involved. So for a question like this, it would be, okay, I've got these 5 tiles in the end that need to be fixed. What do I need to do? Do I need to 3 cycle some of them? Do I need to 2 cycle some of them? And you would just say, much like you would do on the sort of the swap puzzle at the very beginning of the term, you would say, well, I need that 3 to go to where the 5 is. So if I could send the tile in position 2 to position 3, and the tile in position 3 to position 5, and the tile in position 5 to position 2, I could do that 3 cycle, 2, 3, 5, and that would fix them. So I'd say my move is 2, 3, 5 as a cycle, and then write down what the next configuration is. Am I done yet? Maybe, maybe not. It looks like in this case we wouldn't be, so we need to do another permutation, and you just list what the permutation is, and you'd answer in terms of 3 cycles. Worst case scenario, use 1 2 cycle. And the way you'd perform that 3 cycle is now an implementational issue. That would be, okay, now I need to do a conjugate of the 174, but for an exam, I'm not interested in that because that would require using the applet and try to figure out what your setup moves and whatnot. I want you to think in terms of, like on an exam, the higher order strategy. How would I solve this? I need to use a 3 cycle. This is the 3 cycle I'm going to do, 2, 4, 5, for example, if that was it, or 2, 3, 5, and then draw the resulting configuration. Now the resulting configuration still needs another 3 cycle to solve it. So here's the 3 cycle I do, write out the permutation that you want to do, and so on. Does that make sense? Sort of higher order strategy rather than the nitty-gritty implementational details. It would be essentially what would be going on in your head as you're looking at this. You're like, oh, I really want to cycle those 3. Well, just write down, that's what I want to do. I want to cycle these 3. Yeah, exactly. Like question 3 from the assignment. You got it. All right, so it looks like I'm going to have to shut the poll down now. So I'm going to shut the poll down. And feel free to fire in a response if you haven't done so already. And then I will just show you the go ahead solve for this. Yeah, no, not on the exam. I wouldn't ask you to think about the R and T moves in your head. No. So here we go. So I'm going to stop the poll. Ends up being Wise Weasel. I will just indicate. So this was 4, 3, 5, 1, 2. This is how you would do it on an exam. So there'd be 4, 3, 5, 1, 2. There's our turntable. It doesn't really matter. There's all the other numbers around there. 4, 3, 5, 1, 2. Yeah, okay. So the first thing you would do is say, I would like 3 to go there, 5 to go there, and 2 to go there. Okay, that's maybe the first thing I want to do. And that would produce a result that has 2, sorry, I drew the arrow too long. That 2 has got to come right back there. Okay, so then the result is a 4, a 2, a 3, a 1, and a 5. And so that's the first thing we get. And maybe I'll indicate that the way we got that was we did the move, which was to send the object in position 2 to position 3, the object in position 3 to position 5, and the object in position 5 to position 2. And then the next move would be what? Well, I'd need to, in order to solve this, I would need to swap these 2. So I need to do a 1, 4 swap because that's where the position of the tiles are. So my move would be a 1, 4. And then that would be a solve. 1, 2, 3, 4, 5. And so solved, yay. We've solved the puzzle. Now, that would be my strategy. My implementation, which is what I can't ask you to do on the exam unless I had you use an applet and whatnot. But I didn't want to go that route because what happens to the applet's not working for some people and it is for others. So I didn't want to put that dependence on this. So what is the move? You'd say, okay, to solve it, I need to do this 3 cycle. I do a conjugate of that on the actual puzzle itself. Okay, conjugate of sigma 3. Whatever the details are. You don't need to put that in the exam. You just 3 cycle will get you to that step. And then I better be sure that I have to use a 2 cycle. I don't want to use them if I don't need to. And so the first step would have been to note that this is an odd permutation. So yeah, you're going to have to use 1 2 cycle. So that's how I would expect you to sort of do it on the exam. Yeah, so now the implementational details, it could differ from what we've done there. That's our theoretical solve, but you're right, there's a few ways to do this. So let's just finish the solve. So on this puzzle, some of you said you do a turntable move. That puts a lot of stuff home. So that's an option, do a turntable move. And now we just need to swap the 5 and the 2. And so in order to do that, I notice they're already gapped 2 apart. So I can bring the 5 and the 2. Oh, I want them to be gapped to 1 apart to swap them. So I've got to bring maybe the 2 into one side of the turntable, flip it over. Now the 2 and the 5 are gapped 1 apart. Now I can do my D move, which swaps them. And then I can undo that and solve it. And then we get the wise weasel. Congratulations, that's the passphrase. I will indicate another way we can probably do this. And that is, as soon as we did the turntable move, I'll do it here, the turntable move, we notice we need to swap the 5 and the 2 to finish up. But that means before I do the turntable move, 5 and 2 are already spaced apart to do a 2 cycle. So maybe the very first thing I'll do is shift them over, 2 cycle them, shift them over, 2 cycle them by hitting the D key, shift back. Now 5 and 2 have swapped positions and we're perfectly set up for a turntable move. And so there's another way to solve it. So implementation of our strategy could be to do this, or we could to answer in terms of 3 cycles and 2 cycles like I did over here. And so this is the kind of thing you would have on the exam as a response. All right, I'm going to stop the recording here just so that class is over officially.